All right, Mr. Muscarello coming at you with 6.2 natural base E. Natural base E is irrational. All right, means it goes on and on and on forever. It is defined as follows. As x approaches the positive infinity, 1 plus the quantity of 1 plus 1 over x to the x power approaches natural base E, which is approximately 2.7182 and so forth. Okay, so this is what it would be as a decimal. It is irrational, so it is going to go on and on and on forever. Okay. Next, concept 1. We are going to simplify natural base expressions. All right, simplify the expression. We have the natural base e to the third power, or natural base of 3, times natural base of 6. And since I have like bases, what you're going to do is just go ahead and add the exponents. So that gives me the natural base, of 6, that should be 6, of 3 plus 6 is 9. And then all I'm going to really do is just take that and plug it in my calculator. So it's right there at the ln, but you're going to have to hit second ln to get the natural base. Plug in 9 and parentheses, hit enter, and you see I got 8103.08. So that's approximately 8,103.08. Same idea here. 16 divided by 4 is just going to give me 4 on top. And then when I have like bases and I'm dividing, I subtract my exponents. So it'd be 5 minus 4, which is 1. So that gives me 4e, or natural base e to the first power, which we're just going to plug it in just like that. 4 second NL, put 1 in there, in parentheses, and you get 10.873. So that's approximately 10.87. And here I have basically a power of power. So I got a 3 to the power of 1. I'm going to go ahead and distribute that 2 to that, and then that 2 to that negative 4x. So I get 3 squared natural base of negative 8x. All right, 3 squared is 9. And then that natural base, since it has a negative exponent, it's actually going to go in the bottom of my fraction. Take out that negative sign, and voila, I got 9 over the natural base e to the 8x power. Okay, what I'd like you to draw is try number 2. Pause it, give it a try. I'm going to go ahead and show the answers right now. All right, there we go. There are our answers. I'm going to keep on scooting it up here. Check out those answers. Pause if you need. I'm going to go ahead and go over natural base functions. A function in the form of y equals a times the natural base of r times x. As an exponent. All right, so this is called a natural base exponential function. All right, and if we have a is greater than 0 and r is greater than 0, then that is exponential growth. Okay, so here's our parent function, or our most basic function, y equals e to the x, or natural base of x, and that goes up. All right. If a is greater than 0, but r is negative or less than 0, then that would be a decay. And then that looks like y equals natural base of negative x. And that's where it comes down like so. All right, so what we're going to do is go ahead and graph some of those. So I'm going to flip it up. And as you can see, I kind of already started by just getting us the idea with a table and getting us ready to go. So concept 2, graphing natural base functions. Tell whether each function represents exponential growth or decay, then graph the function. All right, so again, what I'm going to do is really just identify a being 3, that's greater than 0. In this case, it's 1 times x, right? So r is 1. Since they're both greater than 0, that is growth. All right, now here's my y-axis right here, here's my x-axis, and what I really want to do is just keep the numbers I choose for my x close to my y because it's exponential growth and it's going to grow really fast. So I'm just going to use -2, -1, 0, 1, and 2. And basically when you do that, you're going to have to plug these all into the calculator. So it's 3 times the natural base e to the -2 power, which is going to give you 0.4 when you plug it in your calculator. And then so forth. So just plug them all in. Here are the numbers that you should get. And you notice once I get to 2, it's 22.2 and it shoots off the graph. Okay, I'm going to plot these in. So -2.4, that's 2 to the left, 0.4 up. -1, 1.1, 1 to the left, up 1.1. 0, 1, 2, 3, 0A. Right? Then I have 1, 8.2. So 1 to the right, up 1, 2, 3, 4, 6, 7, 8.2. And then 2, 22.2 is off the graph. So it comes like this. It's getting this, actually, this x-axis is your asymptote. So it's going to get really close to the x-axis, but never really touch it. And then it's going to shoot up really quickly, kind of even off the graph. And that's what our exponential growth or our natural base growth would look like. All right, second one, B. A is 1 right there. R this time, though, is -0.5. And now since A is greater than 0, but R is less than 0 or a negative, right, that means it's decay. So it's going to go down this time. All right, so here's my y-axis, my x-axis, right? And it's going to get close to my x-axis. Since I have r being a half, I'm actually going to go ahead and double those. So I'm going to make it -4, -2, 0, 2, and 4. Because it's going to be cut in half, then it's really going to kind of be the same. All right, so again, you're going to plug this into your calculator, it should be fine, even though you could take out the negative and put it in the denominator as well, but you could just use that negative, it should be fine. And then plug it in and you're going to get 7.4, 2.7, 1, 0.4, and 0.1. Okay, and now I have -4, 1, 2, 3, 4 to the left, up 7.4, 1, 2, 3, 4, 5, 6, 7.4, -2, 1, 2, up 2.7, 1, 2, 0, 1 right there, 2.4, 2 to the right, 0.4 up, and 4, 1, 2, 3, 4, 0.1 right there. And now it kind of shoots down towards that x-axis and rides kind of right above it, because again, that x-axis is like our asymptote. There we go. There is 3, A and B. Go ahead and try number 4. I'm going to go ahead and show you the answer, so please pause. All right. There we go. There are answers for number 4. And I'm going to move on to the next page, page 7. And we have continuous compound interest. All right. When the interest is compounded continuously, the amount A is the amount after t years. So A equals P, which is going to be our principal, times the natural base of R, which is our annual rate, and is a decimal, times t years. And that's going to give us A, our amount. Okay, so concept 3, modeling with mathematics. You and your friend have an account that earn annual interest compounded continuously. The balance A in dollars of your account after t years can be modeled by A equals 4,500 natural base of 4 hundredths times t. The graph shows the balance of your friend's account over here. Which account has a greater principal? Which account balance which has a greater balance after 10 years. All right, so let's just start with us. All right, let's start with this one. So A equals 4,500 natural base of 4 hundredths times t. And basically, I know my principal right there. So 4,500, I'm going to just kind of let that be for now. And then what I know is t is 10 years. So now I got this 4,500 natural base of 0.04 times 10, which gives me 4,500 natural base of 0.44 tenths. And then if I plug that all into my calculator, I get A is approximately $6,713.23. All right, and my principal was $4,500. So that was of me. Okay, my friend. Well, I can see the principal is right here. That's where it starts at $4,000. There it is. So I have a larger principal than my friend. The next question is at 10 years, right there, how much do I have? And I'm not totally sure, but there's 6,000 and it has to be over 7,000. I'm going to say about $7,200. All right, so who has more after 10 years? Well, my friend, because I have $6,713. So you have a greater, right, when I said I mean, it should be like you. You have a greater principal. At 4,500, but your friend has the greater balance after 10 years. Okay. Number 6 is really basically using this problem. So here you have a new deposit, and then you're going to go ahead and compare it. Okay? Actually, just what is it after 10 years? Okay, so go ahead and give that a try. And I'm going to go ahead and show the answer. All right, here we go. Pause if you haven't finished it. Here you go. There is the answer. And that is all the notes for 6.2.